Good afternoon, everyone. I'm very happy to have the chance to present some works about the construction monitoring using LiDAR technology. In this presentation, I'll be focusing on the tunnel and also the power transmission facilities. I think those are the two quite popular construction. We are using LiDAR to monitor the safety in China. And my name is Zhizhong Kang from the China University of Geosciences. Okay, next. Thank you. I would like to figure out the construction modeling quite popular is the slope deformation and also the bridge and the factory plans and also the power line monitoring and also tunnel monitoring. And as discussed with CC, the environment in the mining areas is also a very interesting target to monitor it with LiDAR technology. Okay, next. So I figured actually we have quite a lot of sensors to acquire the three-dimensional data sets. Okay, we have LiDARs and the satellite-based, airborne-based, vehicle-based, and let's see the handheld and also backpack. Quite a lot of sensors. Besides the LiDAR technology at the moment, photogrammetry become popular as well for the 3D point cloud acquisition. And in China, we call the optical photogrammetry is very popular for the urban modeling. Because using the optical photogrammetry, we can acquire the information and also the facade for the building. So, which is very important for the details reconstruction of the building models. And also, there's one way to acquire the photogrammetry images is we call the object-oriented photogrammetry. So there's two very famous, let's see, the campaign for such kind of photogrammetry in China. And so in China at the moment, if we considering the 3D point clouds, we can reference either LiDAR and also the photogrammetry. Okay, Jack, next. Thank you. Consider the indoor. Actually, we have some very special data set, like the two-dimensional joints from the construction of the building, and also the CAD, and also we can have SLAM and the structural motion way to have the indoor data set. I would say indoor acquisition of the three-dimensional point clouds. I think the question is more complex because it's not like the outdoor, because outdoor we can use the very flexible way to acquire the large-scale data set, but for the indoor, it's more difficult because we have to travel along the trajectory in the indoor space. So which means the acquisition of the data sets is more time-consuming, and also the economic costs will be higher than the outside. So this is the situation at the moment for the indoor data connection, and also the accuracy is a big issue for the indoor data set. if we are going to have a very high precise data set, which means we need to use the very precise sensor with a very good data processing method, and which means that would be maybe it's not so severe problem for the time, and also, but it's also for the economy cost. Okay, Jack, next. Here's some the platforms we can use to acquire data sets for indoor and also for the underground scenarios, like the robotic-based, the track-based, the backpack-based, the handheld-based. I would see that the handheld-based, this way is now is getting more and more popular in China to acquire the indoor data sets. And of course, the accuracy, we are not expect much higher accuracy for the normal LiDAR technology, but handheld is quite flexible, and you can even scan the more dangerous or more imaginable scenarios in the underground. So I think that the platform can be very flexible for indoor and underground scenarios. Jack, next. So I would like to have the presentation on the 4 parts of the construction monitoring. And at the first part, I would like to say something about the Pointcloud procession, because model detection from the Pointcloud is always important for the Pointcloud dataset processing. And the second part, I would like to say something about the tunnel monitoring and also the power transmission facility monitoring. And finally, have some conclusions. Jack, next. I just showed multiple sensors for the 3-dimensional data set acquisition, but different way they have a different quality of the data set. So the normal LiDAR, let's say the terrestrial laser scanner, they have very good precision, and also the handheld scanner also have a good precision. But some cheap sensor like the Kinect, they can have the 3-dimensional data set, but the quality obviously is low. So which means if we are doing the data set processing, different quality data sets may cause the different may cause the difficulty to have a good processing result. So which means we need to do something in the algorithm level to improve the processing of the data set. Next. So for the Pointcloud processing, normally we were involved like the registration. I'm sure everyone knows the registration. It's a way to have the uniform coordinate system or unified coordinate system, which can have the description of the entire objects in one coordinate system. And also the fitting of the primitives, which is also very important for the data processing, and like the image to scan registration. So for all the process, we need to detect model from the Pointclouds. The model can be the transformational parameters between 2 scans, and also the object, the geometric model for a specific feature like a plane, cylinder, sphere, and also the transformation parameters between imaging, 2D imaging and 3D scans. So all the models we can detect from the point clouds with the raw points coordinates. Next. Okay, I just a quick look for the algorithm we developed in the past. This one is the work from the beginning. I worked in Delft for the Pointcloud registration, which using the reflectance images to finish the job without using the camera images. And that's one advantage. Using reflection images, we can incorporate some three-dimensional constraint to try to find more correct corresponding points to calculate the parameters with high precision, like the distance invariance, which can be a very good constraint to have a very good result. And next. And besides, we improve the searching strategy within the ICP strategy. Instead of using KD tree, we use the two-dimensional range image to improve the searching strategies, which shows our proposed method can have very high computational efficiency and compared to the ICP using KD trees. Next. And for the registration, I would see, especially in the indoor and underground situation, because the scenario is quite limited. So if we have multiple scans of the point clouds, we need to have optimized registration results. We call the global registration. So the global registration, there's different way to implement such a process. And there's one way quite popular is we can use the graph. The graph can be some optimized graph, and also the circular can be one, because we have, if we have a circular closure form, so we can have the very strong constraint for the closure of the whole scans. So in this way, we can optimize the global registration results. Next. And actually, we're not able to always find the closure constraint in the scenarios. So we consider the registration process as a stochastic system, and we are going to process to recursively estimate RTPS. So we consider the global registration as an augmented extended information filter. The extended means we can consider a nonlinear system, and the augmented means we can consider all the scans added together to optimize the result. And also we develop a multiple features opposition model. Besides the points, we can use linear feature and the planar features in this system to try to optimize the registration result. Next, please. Here is the comparison of the three data sets. We can see before the global registration and after global registration, we can see a very high improvement of the accuracy for the global registration. Next. Okay, next. And also, we have the global registration also in the tunnel. And I would see in a tunnel, especially for the shield tunnel, we can have a virtual feature for the tunnel is the central axis. So we consider using the central axis as a very strong constraint to optimize the rotational parameters for the global relaxation. We also had a very good result for this scenarios of the global restriction. Next. Jack, next, please.
Possibly there might be a lag. Are you looking, can you see the right slide?
Next, can you move to the next slide? Oh, it was frozen?
Yes, maybe there's a connection problem. Right now I have a slide of the Kinect, which is current.
Okay, you can move all the action on this slide. So I can start to talk on this slide.
This is the Kinect slide.
There's some several pictures on this slide. They showed one by one.
Okay, I think we've got a time delay. There is okay, so if I move back to image to scan registration, or
okay, so now you move to the images to scan registration. Okay, that's faster than I expected.
Yes, no. I think there's a I think we're having a delay in the video. So your image, could you Professor, could I ask if you turn your camera off? Maybe that might reduce the latency.
I turn my camera off.
Yes.
Oh.
Yeah. Okay, are you still there? Okay, can you see the correct video now? The correct slide?
Slide, this is the primitive fitting. I can see the primitive fitting at the moment.
Okay. Yes, okay, and now you want the slide next. Which slide do you wish?
The slide with the image of Kinect and the Kinect 2.
Okay, this one?
Yeah, this one. This one.
Good. Okay.
Yes. Okay, so this slide showed we can use different sensor to acquire the point clouds in the indoor environment, like Kinect. And next. The Kinect 2, and also next. The Swiss Rangers, which I used in Delft a couple of years ago. So different sensor will provide different qualities, point clouds. Next. Yes. Next. So those point clouds are quite challenging because the quality is not so good. So if we are going to detect model from such point clouds, we need some specific strategy to try to reject the outlines and to keep the correct ones. So next. So this is the common challenge we need to face is no matter image matching, pairwise the registration and the fitting of the primitives, we need to detect correct the model parameters from the Pointcloud. Next. Like the fundamental metrics for the image matching. Next. Or the rigid transmission parameters. Next. And the mathematic model for the features. Next. So actually for such data set, we need a robust estimation of the model parameters. Next. So I'm sure everyone knows the RANSAC. RANSAC is a very popular used strategy to try to find the correct points from the point clouds with quite a lot of enrollment, the wrong points. So this model, this strategy, first they need a model to feed the data points. Like the Pointcloud registration, we use the rigid transformation model. And also the Pointcloud fitting, we use the mathematic model for the specific primitives. Next. And we need a strategy to select the sample subset because the RANSAC is the sample and the verification strategy to try to detect the correct models. And so this strategy, they use the random way to select points. The next. And they need to set the maximum number of iteration for the whole process. Next. Next. I will see, we can see some weakness for the original RANSAC algorithm because it consumes the prior probability for each state point, which means if the data set have a high number of the outlines, the iteration will take much more time for it ended with a good result. So by considering the weakness like this, we develop optimized strategy for the model detection from the Pointcloud. Next. So the algorithm we call the optimized Bayes sample consensus. We call it BASEC, optimized BASEC. So in this algorithm, we use the strategy to determine the prior in-layer probabilities, which means we are using a conditional sampling strategy. In this way, we use a so-called convergence evaluation strategy to figure out the right prior probability for each point. And also, at each iteration, we develop an in-layer probability updating strategy, which ensure we can always have the right points to get involved in this process. And also we use the median of squares to construct the cost function. So in this way, we can realize the model-free strategy of the probability determination, and also we can improve the computational efficiency to a high degree, and also we realize the threshold independent cost function. And next. So this is the principle for the prior probability determination. Because of time, I would like to go in detail next. So here's the overview of the probability updating. Next, we formulate a simplified form of the Bayes theorem. Next, and also describing the likelihood as the probability of the best model. Next. Next. And here's the way we construct a cost function with the least median squares. Next. Actually, we found the optimizing Bayesian sampling strategy can be used in different ways, like image matching, deformation monitoring, and also the primitive fitting, and also the restoration. Next. By comparing with the Ransack, we found if the point clouds contains much more outlines, we can see the much higher improvement on the efficiency comparing with Ransack, which means our algorithm can be very applicable for different applications. Next. So here's the comparison of our algorithm with the Ransack. We have different data set for the planar primitive fittings. For instance, we have more than 10,000 points in a room, and more than 200,000 points for the entire floor, and also millions of points for the whole data sets. We can see the computational efficiency improve with averagely 60%, which means we can use the proposed method to improve the efficiency in a very good way without losing the precision cost. Next. Okay, so the second part, I would like to say something about the tunnel monitoring. Next. Jack, do we have a lag at the moment?
Yes, there should be the tunnel monitoring slide with the trains right now. I'm looking at it right now. Are you still seeing the previous slide?
I'm ready to discuss the tunnel monitoring.
Yes, this is the current slide. There must be a time lag. Can you? Is that?
Yes.
The text here says, so far China has built railway tunnels with a total length. Is that the slide that you can see?
Yes. I'm going to stop. Okay, so the tunnel monitoring is also very important for China at the moment, because China has built many subway tunnels across the country, and so it's very important. We have a very good way to monitor the safety of the subway. Next. Concerning the tunnel monitoring, and we have different way to check the healthy condition of the tunnel. One is the geometric deformation. In this way, we will compute the ring convergence and also the tunnel collapse. Besides, the other part of the tunnel monitoring is the physical diseases. I think this part is kind of new than the geometric deformation. And we will focus on the leakage and the crack, and also other diseases we can see in the tunnels. And so at the moment, we're focusing on the geometric deformation aspect of the tunnel monitoring, but we are working on the physical diseases. But for the physical diseases, we are relying more on the images, I mean the range images, because the physical diseases, we can use the, let's see, the difference of the reflectance to show the physical difference. Next. Okay, here's the very quick overview of the deformation monitoring way. We can have a contact and a non-contact. Next. I'm sure you must be very familiar with the ways, the contact and the non-contact. Next. Okay, from the beginning, when we are considering, when we were considering using the LiDAR to do the tunnel monitoring, we figured out in which way we can use to visualize and to model the deformation. As we can see from these images, we can have a very high resolution point cloud in the tunnel. Next. So we can have the resolution, let's see, with 3 millimeters. So we have plenty of points. What can we use with these points? Next. So we can model the tunnel with a coarse continuous surface. Next. Or can we use the surface to do the continuous deformation monitoring? So this is the question we need to consider. Next. If we have a 3D model of the whole tunnel, that would be easy to visualize the tunnel. But I would see that would be a problem to model the deformation, because if we're going to have a 3D model of the whole tunnel, which means we're not able to accurately to describe the surface of the tunnel in a specific region, which means we're not able to very accurately evaluate the deformation. And next. So the data volume is an issue, because we need to handle millions of points at the same time. Next. And also, we are not able to remain the accuracy if we are using the whole model of the tunnel. Next. So we propose to use the cross section to estimate the deformation of the tunnel. And in this way, we need to extract the central axis of the tunnel and also the cross section of the tunnel. Next. Okay, this is the whole flow chart of the process. We extract the central axis from the Pointcloud, and with the central axis, we extract the cross section, ideally at any location from the tunnel. In which way we use the cross section to evaluate the deformation of the tunnel. Next. Here is the accuracy comparison we conducted in the tunnel of the Shanghai city. We have the average deviation with 3 millimeter, which is can be satisfied with the application. Next. And this is also the access fitting with the global restoration strategies. Next. Besides the deformation monitoring, we also implement a strategy to have a high precision and a high detail model of the tunnel. This is the project where we were implementing in the tunnel in Nanjing City. Next. So we have the time lag, right?
Yes, this is the model reconstruction based cross sections.
We need to go. Yeah, this is the model we reconstructed from the cross section. First, we have the cross section cross-sectional points, and the triangulation is used to construct the model for the whole tunnel. Next. So in this way, we can have the model with different resolution. Next. But the problem is such a model are not able to describe the real tunnel scenarios. For instance, for the shell tunnel, we have different rings and different blocks. But for the triangulation model, we are not able to represent the different blocks. Next. So this is the pipeline of the tunnel 3D modular reconstruction with the block level detailed. And at the beginning, we extracted the axis, and we extract the cross section, and we unfold the Pointcloud into two-dimensional images. And in the images, we extract the blocks and reproject to the 3D. And then we have a very detailed model for the whole tunnel with different blocks identified from the Pointcloud. Next. This is the strategy we use the range images to extract the different blocks from in terms of the reflectance difference. As we can see from the right images, we can easily identify the different blocks. So in this way, we can use like computer vision and also the deep learning strategy to extract the different blocks from the range images. Next. So those are the identified blocks from different rings. Then we reproject into the 3D model. Next. So we can see for such a tunnel model, we can identify each block at the specific ring, which I think in this way we can have a very good input for the beam model for the tunnel. Next. Okay, those are the blocks we reconstructed from the Pointclouds in the 3D. Next. So we have reconstructed 3 tunnel model for different cities. So they can be used for the beam model, for the facility management, and also for the safety monitoring in the future. Next. Here is a system we are developing with the LiDAR and the IMU unit, and also with the SLAM, the algorithm, and we hoping we can use it in the real application in the future. Next. Here is the configuration of the hardwares. Next. And we besides the data processing, we incorporate the IMU to try to extract more accurate central axis and also the cross section. Next. And this is the flowchart of the whole process. Next. Okay, and the third part is about the power transmission facility monitoring. Next. And actually, LiDAR is become more and more popular in the transmission facility monitoring, because it was proved a very efficient way to acquire the data set for the transmission facility, like the transmission lines and the pollen. And so those data sets are very important for the safety in estimation for the facilities. Next. So those are the description of the application of the Pointclouds can be used in the safety monitoring for the transmission facilities. Next. And if we are going to evaluate the safety of the facility, we need to extract those from the Pointcloud first. And for this purpose, we need to face 2 challenges. One is, at the moment, most of the algorithm to extract the transmission lines is based on the assumption a line is linear. And basically, it's true for some cases, but if we are discussing the high voltage transmission lines, we often have the split conductors, which means we're not able to describe the split conduct with a linear model. So this is one issue we need to solve. Next. Another issue is we need to model the different pollen, but the pollen have different shapes. So if we are going to have a reconstruction automation, and we need to develop more common algorithm to do the job. And so as we can see from this slide, normally we have double conductor, 4 conductor, 6 conductor, and 8 conductor. So if you are extracting the such conductors, we need to try to find a way to Okay, so the slide is moving faster than I presented, Jack.
Yes, sorry, it seems to be automatically progressing.
Okay,
yeah.
So I can try to be faster. We found the strategy, the skeleton structure analysis is more efficient in this way. If we conduct the skeleton structure analysis, we found we can reduce the radius of the power lines in this way. As we know, if the radius becomes smaller, and the power lines can be described in a linear feature. So in this way, we can use the skeleton structure analysis to extract the transmission lines in this way. Next. So this is the comparison of the transmission line extraction with other method. We can see we can have a higher accuracy comparing with the other method, but because we were using the skeleton structure analysis, which is in the iteration way, so we lose some computational cost. So this is one disadvantages comparing with other method. Next. And in this way, we can reconstruct the realistic 3D model for the transmission lines. We conduct this process in two steps. One is that we model the horizontal aspect of the power lines in a linear function. And in the vertical way, we use the dangling line model to feed the transmission lines. So this is the process we use to model the dangling line of the transmission lines. Next. And actually, it's not that easy to have a correct transmission line in 3D. So we use two strategies to have the optimized results. One is we use the 3 data principle to reject the fake models, and we use the nonlinear least squares estimation to try to have the optimized the transmission line model. Next. Okay, those are the transmission lines we reconstruct.
We've just lost your audio, Professor Kang. If we've just lost you for the last few seconds.
Yes, I come back.
Okay, we can hear you now. So we're still on this slide, realistic 3D.
Okay, next. Okay, those are the pipeline we reconstruct the Pointcloud model, and we divide the whole structure into 4 parts. For instance, the poly head, the poly body, and the cross arms. So we parameterize the different parts, which can improve the degree of the common we can use to reconstruct the different shapes of the poly model. Next. Okay, those are the comparison with the different methods, which improve. We can have very good extraction reconstruction result for different types or different shapes of the point model. Next. Okay, those are the reconstruction result for different point models. So in this way, we can have a very high resolution and high accuracy model we can use in the safety estimation and also the monitoring process. Next. Okay, besides, we also use the UAV for the landside monitoring. Okay, next. Just a quick overlook. We use the UAV to have the image acquisition. Next. And we can use the images to create the DOM and DM. Next. And sorry, we're not able to see the video. Next. So those are the products we can have from the image processing. Next. So based on the models we acquired in different time, so we can detect the change and also the deformation for the body of the stand. Next. Okay, so at the moment in my university, we have a group of geomatics and remote sensing. At the moment, we have 12 faculty members, including 2 professors and 9 associate professors. So our background are diversities. We have photogrammetry, LiDAR technology, INSA, GNSS, and also immersion and deep learning. So we are kind of a hybrid faculty groups. So we can have very interesting project to try to improve the application of the LiDAR technology. Next. Okay, those are the equipment we have at the moment, and I will see we can have very interesting works with such equipment. Next. Okay, next, the conclusions. I see for the construction monitoring, the single sensors is not able to do a quite a good job. So we need multiple platform sensors integration to do a very good job. And also because we are handling the data larger and larger, so we need big data and immersion deep learning techniques to try to improve the accuracy and the detail of level, and also we can have some imaginary works in the future. Okay, so this is all my presentation. Sorry for the connection problems. Your question are warmly welcome. Okay, thank you.
Thank you very much. That was an excellent presentation, very interesting, and lots of fun too. Lots of excellent machines and visualizations of the very interesting work you've been doing. So thank you very much, Professor Kang, and please, anyone, if any questions.
Okay, and we have quite some, yeah, thank you very much, Professor Kang. It's really very detailed and very interesting presentation. And we have some students that have been using a lot of Ransack. Mudan, would you like to say something about your research and ask questions?
Hi, Professor Han. Thanks for your presentation. It's very interesting. And I also used the Randoc and the region growing for my research. And what I did is about the quality check on the construction site. So most laser scanners I used is terrestrial laser scanners. And from your research, I saw most of you use the like mobile laser scanners for the tunnel monitoring. And I want to know if you like based on your research, have you used the beam model for the comparison with the data you collected, or you just made the point cloud data processing on the data you collected from the real sites?
At the moment, we only use the data set we acquire from the site,
Mm,
and we are not using the documentary as built.
mm,
And as I mentioned, because actually we already like the shell tunnel and operating tunnel, they definitely they have their documentary for the tunnel. So I think which can be a very good combination. We can acquire the model, the realistic model from the Pointcloud, which is the real time. We can use the model to update the documentary, and also we can as I mentioned, we can use it as an input for the beam model for the tunnel, so which we can keep the currency of the model. I think this is very important for the operating tunnel for the safety monitoring purpose.
Okay, thank you. And another question, and I saw that you also develop some algorithm for the plan fitting, and you compared the method you proposed with the Randac, and you find that the proposed method could be more efficient than the Randac on the
Yes.
data set with higher outliers levels.
Yes.
Right? So
yes.
how you did this kind of experiments? So you used some data set with different outliers levels for the comparison, right?
You mean the data set I choose?
Yeah, because you did some experiments and then you made the conclusion that the proposed method is more efficient than the Randac on the data set with a higher level of outliers. So
yes.
you use the data set with different noise levels.
Actually, okay, the noise level is one aspect you use to evaluate the performance. Another way is for the point clouds, even with a higher quality point clouds. We will say if we are focusing on the one features, for the other points they are outlined for this feature.
Oh yeah, yeah.
So which means those are the run points for my estimation of this feature. So we can use this way to compare the performance between the Ransack and my proposed method. And the outlines is not we will not see the outline is the noise, but the outlines can be the points. They don't belong to the feature of interest.
Yeah, I understand. Thank you. Thanks for your presentation. Thank you.
Okay, so actually, I would feel much happier if you are glad to use our proposal method to do the experiments to improve efficiency. Yeah, for your work.
I'm glad to have a try because now I'm using Rundeck for the plan fitting, and yeah, I'm happy to try more different methods to see the efficiency improvement.
Yeah, as you can see for the slide I mentioned in my presentation, we do see very high efficiency improvement for the planar features fitting, because planar feature is very important for the indoor modeling.
Yeah.
Yes.
And you also need the parameters estimations. I mean, for different data set, you need input different parameters, or you can use the same parameters for your method.
For RANSEC and BASIC, they are not parameters dependent. The strategy, they are not parameter dependent. And actually, of course, the RANSEC need the threshold to evaluate the quality of the model. And in my algorithm, we use the least median squares to construct the cost function. We try to reduce the influence of the threshold because the threshold is not objective. So it depends on the quality of the data set and the models. So yes, we can test the performance in the future if you are interested.
I'm interested. I'll have a try.
Okay.
Thank you.
Okay,
okay. You can get in touch with me personally with Professor Kang. I was also going to suggest just to use the alternative RANSAC that they, or plant fitting that they have developed, and to check with your results is going to be interesting because now you are actually trying to adapt the parameters of RANSAC, to investigate which parameters are going to be best for what kind of prefabricated platforms.
Yes.
Yeah. Okay, so Ben, do you want to ask something, Professor Kang?
Hi, Ben. I couldn't see you.
Hi, Zhizhong, how are you?
Hi, I'm fine.
Very nice to see you.
But I could, okay, long-time see. Here you are.
Very nice to see also Hu Ming and Jochem in your presentation. I didn't expect that.
Yes.
I had a question in mind, but in fact it was the first question that Mudan was asking about whether you use the available information to check the models with. I have a very short other question. Were you talking about estimating the parameters of a power line, about the wire itself, or did I understand that correctly?
You mean the estimation of the parameters of the power, the transmission line, right?
Yeah, the line itself, the hanging thing.
Yes, dangling.
Such a piece of line, it has only one parameter, is that true? If you know the beginning and the end point, then all you need to know is the length, I assume. Is that correct or not?
Actually, we are not only use 2 points. The 2 points is one try. We we were trying different 2 points, different sets of 2 points, and we try to with the multiple, which means we have multiple tries. We try to fit out we believe the correct ones. So we are not using one try, 2 points to get the
2 points. Okay.
2 points is one try.
And then the length of the wire, I think, is that's the whole parameterization, or am I wrong? Can you see whether they nicely hang in a parabola, or didn't you check that?
Let me check. Let me check. Can you see the we have a chart to show the dangling line model. Actually, we have
any slides.
Probably, Jack, you can share again the slides.
Yeah, to the page 58.
Okay, I'll try to do this as quickly as I can. Please keep talking.
Maybe it's also not that important. I mean, I was just curious. It's
okay.
Actually, we have a tangent equation. Okay.
I was planning to ask a question. Okay, before Jack starts the presentation, I was wondering, do you use sometimes voxels when you do the processing?
That's a good question as well. I mean, when you say skeletonization, is that with voxels, or is it something else?
Voxel, yes. Actually, we are using voxel for the Pointcloud processing.
And skeletonization, do you have that? Do you have a point cloud routine for that, or a voxel routine?
Yes, I would see a voxel is the basic element for our processing of the Pointcloud. We're not using the raw point.
So you're converting everything first to voxels, and after that you do the processing.
Yes, yes.
Oh, okay.
But why don't you put here and there the word voxel in your presentation? It makes it very nice.
Okay, so because the time is quite short, and okay, I have a couple of papers I can send you for if you are interested, because voxel is quite element, the elementary process.
Great.
Yes, this.
Here is the okay.
Yes, this is the model we use to estimate the tangling line model.
Okay, this first formula looks like a Huff transform, but it's not, I guess. It's a plane. Okay.
So each time we use 2 points, but we will try many times and try to, as mentioned, Jack next. Yes, we because we have different tries, so we use the 3 data principle to try to rule out the wrong estimation and use the nonlinear least squares estimation to try to get optimized result.
But you are fitting then a parabola, are you?
Yes.
Okay. Yes. Okay, thank you.
Good. You're welcome.
Okay, so do we have some more questions?
Hello.
I always have questions. Can I ask, how do you define the center line of a tunnel?
Oh, yes, that's a good one.
The central line of the tunnel, actually, basically, the basic way is we project the tunnel, the 3D tunnel, in two directions. So in each direction, we will have we can estimate a central axis in such a projection, and we use the two projection, reproject to the 3D model to try to feed the virtual central.
Wait a minute. In order to do the projection, you already have to know the center line.
I estimate the center line in terms of the control of the tunnel projection in a certain direction.
In a certain direction, but which direction is that?
It can be the X or Y or the X or Z. So we project the 3 dimension in this direction and in this direction. We will have two-dimensional projection. On each projection, we will have a control of the shape of the tunnel. Okay. So we use the contour to estimate the central axis in this way. So okay. I would see along the central axis, we always have a direction perpendicular to the contour of the surface of the tunnel.
Okay,
so in this way, we estimate the central axis.
Thank you.
Because we need to have a very accurate central axis. In this way, we can have the correct cross-section of the tunnel. Yes.
Yeah. Okay. Thanks.
You're welcome.
Han wanted to ask something.
Yeah.
Han, go ahead.
Yeah, thank you, Professor Kang. Thank you for our presentation, from which we can learn a lot. I am doing some research about tree modeling, and I noticed that when you do some about the power line, we segmented the trees and the power lines. Could you please share more with us about how to segment the trees and the power lines? Because sometimes power lines are very close to trees, and sometimes they even go through the canopies. So, did you meet some difficulty in segmentation of these two objects?
Okay, so for this problem, for this issue, actually, we often facing the challenges in the stage of the Pointcloud classification. As you mentioned, the trees and the transmission lines, if they are too close to each other. But first, we need to do the Pointcloud classification. Pointcloud classification, we can use the machine learning or the deep learning way to try to have a very good result for the classification. In this way, we can figure out which point belongs to the trees, which point belongs to the transmission line. This is the first stage, and the second stage is the linear feature extraction, because the transmission line they follow a certain linear features, so we can use the feature to figure out the sum. But actually, if the transmission lines get quite close to the trees, or even they get together. But I would see that would be very dangerous, because we need to have a safe distance between the transmission line and the trees. And when not expected, they get quite close to each other. So in the algorithm level, in the algorithm aspect, we can consider if the transmission lines close the trees, or maybe they are together. We consider how to figure out it. But in the realities, I don't think that would be possible, because this is the purpose we do the safety monitoring. And if they are getting closer, we need to do something to let's say cut down the tree to keep the safe distance for the transmission line. But actually, for the algorithm, we try to do a good classification for the point clouds to try to figure out the tree points and the transmission line points. And then we use the linear feature to try to figure out. But actually, that's one big issue, is the tree points, always the number of the tree points is much larger than the number of the transmission line points. I think this is very bad for the classification of the point clouds, because the tree points dominate the number of the points, so they always have a strong influence on the network of the machine learning or deep learning. So this is always a question we need to think about. It wouldn't be so easy, but yes, we need to face it.
Yeah, I see. Thank you.
And Ibrahim, you have your hand up.
Yeah.
Sorry, the mic was mute. Very interesting, and thank you, Professor Zhizhong, for the excellent presentation. I only have a question regarding the data quality and resolutions for tunnel monitoring. So I noticed in the presentations you detect the block, but what about other kinds of deformation, like the cracks? So is it the resolution, data resolution can be used for this kind of detection, like crack detections or pillar detections?
Thank you. This is a very good question. As I mentioned at the beginning, for the tunnel monitoring, we can have two parts. One is the geometric deformation, and another is the physical disease. I would see the cracks. We need to classify into the physical disease. For the cracks, we need to have the high resolution data sets. Otherwise, we are not able to figure out the cracks. And for the cracks, actually, we can use the range images as a way to figure out the cracks. And also, I would see we can use the deep learning strategies. But actually, we need to have the sample database. I would see the bigger the sample database we have, the better performance of the deep learning method can be expected. So for the cracks, I would see we can use the machine learning or deep learning way to do it. It's only the geometric deformation we can use the cross section to evaluate it. But for the disease on the wall of the tunnel, we because we have a huge data set, that would be quite difficult to use the normal way to detect the cracks. So actually we need to use the machine learning or deep learning way to do it. But for that, we need to have a very good sample data sets, because this way actually depends on the sample data set.
Thank you very much.
Thank you.
Okay, so this
Zhizhong,
was
Zhizhong has
Jim.
a hand up. Yep. Zhizhong, do you have a question?
Young.
Can you hear me now?
We can hear
Yes,
you very quietly.
But we cannot see you.
Oh, okay, yeah. I hope now it's working.
Yes.
Okay, good. Yeah, thank you for the presentation. I can see a lot of development. I just have a follow-up question. So you just mentioned we need a sample to detect the cracks or some physical disease. But do you have any idea how to create these samples? And because I can imagine, yeah, it's very difficult to get these samples. Or maybe you need some people to, I don't know, to label the point clouds, or I don't know, or maybe you have to look at the images to, you know, to label the images. And I don't know, just asking.
Okay, thank you. It's a very good question. Concerning the samples, actually we can have it in different ways. First, we already have the detection in the past. I think definitely we will have such documentaries, because it can be detected by the people or by the force to have the cracks in the tunnel. Then we have the point clouds for the tunnel. So which means we have some prior samples before we acquire the data set for the tunnel. But the documents definitely can be a way to have the samples in the point clouds. I'm not sure if I make myself clear, which means in some tunnel, we already know where are the cracks are. So, which means we can figure out them in the point clouds. So we can have the sample. This is one way. Another way is we can try to figure out some cracks in the point clouds. But either way only be able to have a very limited samples. That's for sure. So we have two ways. One is we try to accumulate the samples, bigger and bigger. Another way is we can try some network. They claim they have a good performance for small sample data sets. So this is another way, but I'm not able to answer you if it's possible to have a very good result, because we just start to work not very long time. But I'm sure that the sample data set, if you accumulate, is bigger and bigger, you must have a better result in the future. But besides, you can try some network. They claim they have good performance on small sample data sets. So this is the way I can imagine at the moment.
Okay, thank you. But maybe some thought from my mind, because I was thinking maybe we can combine point cloud with images, yeah, with photogrammetry, and just use some.
Yes,
images.
definitely.
Yeah.
As I mentioned at the beginning, for the physical diseases, we definitely need to use the range images to do it, not the real point clouds.
Okay.
Because
Yeah.
the reflectance value can reflect the physical attributes to some degree, like the linkage. Definitely, we can find the feature of the linkage on the range image because the linkage make the region wet, so we will have less return signal compared with other parts. So that's what I mean. We definitely need to use the range image, not the pure coordinates.
Okay. Yeah. Yeah. Thank you. Thank you for the answers. Yeah.
Oh, thank you.
Okay, this was a very nice and very long discussion. It's much longer that we normally have. But okay, we also started a little bit late.
Yes. My fault.
Technical fault. It's nobody's personal fault. Okay, so if we don't have more questions to Professor Kang, we can thank him. And yeah, any other questions, they can be directed directly to him, sent via email or even via WeChat. Some of you can exchange with him his
Okay, no problem.
WeChat.
Yes.
Okay. So, Jack,
Great.
back to you.
Well, yeah, thank you very much, Professor Kang. And well, if everyone maybe could turn their cameras off if you're presentable, and a round of applause. Thank you very much.
All the cameras
Okay,
on.
thank you.
All the cameras on. Put the cameras on.
Thank you. Thank you.
Thank you, everybody. That's very nice.
I hope I can visit you in the near future.
You're very much
indeed.
welcome. Yes. Yeah. As soon
well
as it's possible to travel, you're very much welcome.
Okay.
Great. Thank you very much.
Okay.
Thank you.
Thank you.
Have a nice
So,
day, nice
have
evening.
have a good day. Or maybe have a good evening.
Good evening.
Okay. Bye-bye.
Bye-bye.
Bye-bye.